I just updated website, and this will be our last project. So in the past, we have another one regarding real-time systems, but I don't know where we spent like more time than last year. I just don't have time for the real-time one. But I think let's just take the time to get a good product from this project. Expectations have changed slightly compared to last year. If you click into it and scroll down to the bottom, so we are having so you have to use the Arduino board. It could be the Uno board to build communication with the accelerometer. I think most of you have done that in your CE351, but Jesse hasn't taken that before. So this could take more time than other people probably. But I have all the detailed instruction on this website and somewhere else. It should be very simple to do. You should be able to read the acceleration and gyroscope data in the serial monitor. There's some tricks that I'm going to show you in a bit. Second, be able to use data fusion and complementary filter to report the angle of the MPU module. It's a calculation that you use acceleration data and the gyroscope data to find the angle of the two-wheel balancing robot. I have the calculations in the instruction I'm going to show you in a bit as well. And PID controller is another technique we're going to learn in this project. Build a balancing robot, use a NEMA or NEMA, how to pronounce it usually? NEMA probably. NEMA stepper motor and acrylic plates available in the lab. So which means we're not directly programming the tumbler as a final product. You do need to do that in order to demonstrate the controller and the remote control. Okay, so PID controller is the software controller to balance the robot, and the remote control is the hardware. You have the joystick on it to move the car around. Okay, so that's the different things. And you're going to demonstrate your software and joystick on the commercial tumbler, which is a two-wheel balancing robot that we have in the lab. I'm going to give you a bunch of new ones. If you want to assemble yours, you're welcome to do that. If you find some of the cars already assembled by the past students, you can also use theirs. But we probably don't have that many in there. So the PID controller and the remote control need to be demonstrated on that robot, which is basically just duplicating whatever they have done in the past. And the code and instructions are available. Okay, you can pick up which design you want to use in terms of the software design and use one of them, okay, for the tumbler, and just duplicate it, just make it work. That's, I think that's task 1 to 3. It should be pretty simple, 10 points, 20 points, 40 points as gifts, right? It's given to you. Just need to duplicate it, copy and paste. And then after that, I don't want to keep using the tumbler's DC motor because it's very difficult to find exactly the same motor from anywhere. It seems like they source the parts from some of the manufacturers in China and doesn't even have a part number on it. It's very difficult to find them anywhere in the US. However, the stepper motor will definitely perform better than the DC motor, I'm pretty sure. The DC motor, the tumbler robot has, they have the encoders combined with the DC motor. Seems like the encoder is going to make it more accurate. But the code, including the original code from the manufacturer of the tumbler, they didn't even use anything of the encoder. I was looking at their original code, which was super complicated, but they didn't use the encoder's data at all. So I'm assuming the encoder is not being used. It's just a regular DC motor. So in that case, and I was observing the performance of the tumblers, built by the past students compared to the balancing robot that I built. I don't know how many years ago. That was during COVID. I demonstrated. I had a couple of videos at home, and they worked way better than the tumbler, the commercial tumbler actually. So I believe the stepper motor being used has a way higher quality compared to the DC motors and more accurate, will give you a better result. So I hope in the future, if I'm selling these balancing robot, I will probably want to use these NEMA 17 stepper motor instead of the DC motors, um, to have fewer frustration for the customers when the customers are trying to duplicate it, repeat the work on their side. Um, I'm going to show you the car frames that used the NEMA 17 stepper motor. That was the first time I taught this class and this project that we used the acrylic plates and the rods to build these cars. We still have, I just counted, probably we have 7 to 8 of these car frames that I can directly use. It will save you a lot of time. So you can just directly grab one, and it even has the 3D printed brackets to hold the stepper motor in place on the car frame. So use that one, okay, if you don't want to make your own. And so the final product will be a car frame, acrylic plates car frame with a NEMA 17 stepper motor, and use the RF modules and joystick to control the car. Yeah. Yeah, but
like we literally had to point them to each other in order for them to communicate.
I know there might be some issue
So
with it.
why don't we just use ESPs?
That's-
Because ESPs work a lot better that way.
I know. Yes.
I mean, not even controllers inside yet.
It might be the code, the code of the that they used for the 2.4 gigahertz RF module. Some of because I'm not saying you didn't do well. I'm just saying it's not working as good as the ESP32 that I agree with that. So that's why I was thinking after I upload the tutorial, I was thinking that you may be able to use ESP32 if you want, which is actually even better, especially for the ESP32 cam. So in the future, you got a ESP32 cam controls the car and also at the same time streaming videos. That would be really cool. So you can do either way. You either use RF modules, if you can find a better code to use it, go ahead and do it. Otherwise, you can also switch to ESP32. I believe I have tutorials on that as well, right? So ESP32 with the accelerometer. Remember? I think that was on these ones. Okay, these ones. Yeah, so go back to so that was from the horseshoes project, remember? Yeah. Where I used the ESP32s and the accelerometer. So go back to the last semester's 351 class, find out that tutorial over there. Okay, now let's go back to the details of this tutorial. So for section 1, it's just I just copy and pasted the tutorials about the stepper motor. You don't have to really read all of them. I think you already did it in the last, the one before the last one in the tutorial when you are using the RF module with the NEMA 17 stepper motor, right? So I already did everything in here in section 1, and you don't have to redo it. Starting from section 2, there's instructions regarding the MPU 6050, the accelerometer and gyroscope. And its board has a regulator and a sensor. It's a micro mechanical and electrical sensor, MEMS. Okay, it's Dr. Jessing's specialty here. it has all the micro sensors that can, or actuators that are able to sense the motion. It's pretty amazing. Like you have all these nanowires being built in silicon, and they are moving around to change the capacitance inside the chip. If you zoom in, it's actually a little micro machine in the chip. And you are thinking silicon is just a glass a lot of times, right? You can easily break it. But actually, if you build them in a nano level, they're really rigid. It's just moving around like a wire, like a metal wire or something. It's so when for example you have, and you are using photolithography to make different layers of the silicon wires, and for example you have two wires hanging there, right, in the air, and when it moves, so the macro nano level parts are having a movement of displacement relatively to each other, and it's going to change the capacitance. You know what I mean? So for example, we have two nanowires in there, right? And if there's acceleration being added to the board or to the chip, it moves a little bit, right? So you can see the area in between these two plates will change. The capacitance will change. So since the capacitance are compared to, it's called CDC. It's capacitance to digital converter, CDC. And that little integrated circuit inside the MEMS chip, which is this accelerometer, will convert the capacitance change into a digital signal like ones and zeros. And to indicate the acceleration, there must be a formula to calculate it, how to convert the capacitance change to acceleration. But you can definitely convert it that way, and eventually output digital data. So it's basically converting acceleration into one and zeros. And the reason why I use one and zeros is because it's taking less number of pins. We all know that. And it's definitely using I2C. You can see it's ICL and SDA. And I believe this module already has a pull-up resistors for these two lines for I2C, so you don't have to redo it. Let's take a look at schematic. Yeah, they are. See, 4.7K. It's required. We don't have to know why, because that's designed by whoever invented I2C protocol. So inside the circuit, it requires that ICL and ICL are put up to VDD. And because sometimes you see they use 10K, sometimes they use 4.7K. And you should know that both works for our application, but you can change the resistance accordingly if you are using a different transmission rate. Usually we don't tune it. It only happens to very rare situations that you have to care about the transmission rate. Then you have to choose different resistance over here. But definitely it's still, because the pull-up resistor is always larger than like at least a 2K, I think, 2K, 3K. Cannot put a 500 ohms resistor there. It's consuming so much current and it's not pulling it up to VDD at all. So 4.7K works. You're asking, if I replace it with a 5K resistor, does it work? Yes, it's going to work. It's just a pull-up resistor. If I replace it with a 10K, does it work? Yes. Yes, we don't care about the transmission rate at all. But if you care about it, then you have to do some calculations. According to the probably I2C's protocols manual, if you can find them, how to calculate the resistance. Okay, so that's for section 2. If you scroll down, so this is schematic of it, and keep in mind we're not using the module, so you use the module for the demonstration with the tumbler, with the commercial two-wheel balancing robot. However, we do not use the module for our final design. You have to extract all the information from this, and we have, I believe, everything from this board, and you have to solder the chip, the MEMS chip, and all the peripheral components to your own customized PCB. If you look at the arrows here, okay, so Y is pointing up, and X is pointing to the right, and Z is coming out from the page. So that's X, Y, and Z for the acceleration and also for the gyroscope, which is the angular velocity. I'm going to show you how to calculate it in a bit. So keep in mind the MPU 6050 is a 3.3 volts device, right? Because 2.3 volts, 2.4 volts to 3.46 volts. For gyroscope, it's measuring the angular velocity, which means how many degrees are changing over time. So you can see there are three directions. This is X, rotating along X, rotating along Y, rotating along Z. So spinning around Z. And we have names for them, right? For the airplane design. It's called yaw, this is called roll, this is called pitch, which makes sense, right? Pitch, right? And this is roll, and this is yaw, okay? We need both data, the gyroscope and acceleration data to calculate the real-time angle of the robot to make it more accurate. I haven't compared, but I think it can be a really good research article if you do compare them, right? If you don't use both, just use one, how much difference you're getting from that. Okay, now let's see how we can find acceleration and the angular velocity from the MPU module. So it's a digital chip and it has registers. Every register is a byte. How can I tell it's a byte? 8 bits, you got bit 7 here. You don't have like bit 15. So it's a 8-bit device. But doesn't mean that you cannot have 16-bit data. If you look at the acceleration for X, it's actually combining the data being stored in 3B and 3C. So 3B is the address for acceleration X direction output from bit 15 to bit 8. So that's the upper 8 bits. And for address 3C, it is a lower byte. So you have to combine them two, the two bytes here to form a 16-bit acceleration data for the X direction. Any question by far? And for the ones who have taken microcontroller, it could be simple, but any questions here, Jesse? So what that does is, all these are bytes being stored in the memory, right? You read this byte and shift it and combine with another byte, so to form a 16-bit data. Same to Y and Z. And because all the data being stored in the registers are in what form? So after you run it, you part it up, it's going to start reading, right? If you enable it. And the data will be stored in the register. So these are in what form of data it is? 1 zeros, right? Yeah. Okay, just binary data. So if you want to convert it into acceleration, I think it's the unit is g. It's how many g's. But how to convert it? You have to choose one of the four options here. But you can set it up in a register. For example, we choose the first option. So it's called this many LSBs per G. And because the data being stored in the binary form, the unit is what? The unit. If for example, I have in a 16-bit data, I have like all zeros and then 1 0 0 0. Okay, just 8, right? Just 8. Okay, so what's the unit of it? No, just the data. What's the unit? If I have the binary numbers stored in the 16-bit memory, what is the unit of that data? Hmm? So it's just that many LSBs, right? It's just one LSB is one, right? It's just how many ones? No, how many? Like 5. 5 is 5 ones, right? You know what I mean? Yeah, for LSBs. So one LSB, huh? Just follow, okay? I'm telling you, if 5 is 5 ones. Do you agree with that? No problem with that, right? If it's a binary 5, it's 5 LSBs. The reason I'm trying to let you guys think about that way is because if you look at the unit here, if you choose the first option, it's that many LSBs per G. So how to get how many Gs from the 16-bit data? Yeah, divide whatever you are getting here by this number, right? So your LSB unit will be canceled. Okay, and then you are getting how many Gs, right? So in that case, but very rarely people are using option 1, option 0, but it's the same thing, right? If you choose this option, then you just divide it by this number. And how do you make selections for these bits? It's a very interesting topic to talk about, since when we are programming Arduinos, it's very convenient, it's easy, and have a lot of libraries available. But a lot of times you didn't have the chance to modify the registers, which we used to do a lot in the past to program all these microchip microcontrollers. But now we are doing bitwise manipulation. So if you look at this bit, I actually had a snapshot for you guys to look at. Okay. So it's a 2-bit number, actually. So it's AFS underscore cell, it's a selection. It's a configuration byte. It's a register that controls the functionality of that reading or the number, readout number from that. And it has an address, so you have to configure it if you need a specific option for the 4, one of the 4, right? Which LSB per G you want to use. So you have to read through the I2C protocol. You just write a byte into 1C, okay? So I'm going to ask you, for example, I'm trying to let's see. Just take this one for example, okay? So if I'm trying to have as an option 2, okay, so it's going to be O1. So 1 0 will be the option 2, right? And 1 1 will be the option 3, number 3. If you look at the table, you have 0, 1, 2, 3, 3 options. These are decimal numbers, but in the configuration, you use binary numbers. So this is option 1, 2, 3. If you need an option 0, just put 2 zeros over here, okay? So in the hex form, right? In the hex form, if I want to use option 2, what is the hex number I need to give to this register? If I want to use this option, what's the hex number do I need to give to this register, to this address? What's the number I need to write into this address? So these are not changing, right? So we don't have to change it. Just by default, it's just zeros, right? Okay, and 1 0 because I'm trying to select option 2, right? And just don't do anything for these the rest of the bits over here. So what is the number? Yeah. So it's going to be 0x 10. Got it? Okay, that's how you configure it. That's the address of the device, of the MPU device, because you can have multiple followers. In this industry, people are trying to use leader and followers instead of master and slaves. So being professional, don't use master and slaves anymore in the future, or use followers and leaders. So this one is a follower's address, and if you have multiple I2C devices, you can so they have their own address. You know what I mean? So the accelerometer can be one of the I2C devices, and it can have another thing, has different type of sensor, also has I2C, but being connected to the same bus. So you have to tell the difference, or sending data to different devices by claiming the address first. But we don't have other devices being connected to the bus. It's only the MPU, so we'll just use this one. Okay. So this example code is only measuring the x acceleration values along the x-axis. And keep in mind, you have to reset it. All right, very important. So 6B is 6B the address or the data? Yeah, address. Let's take a look at it. What is in there? What is in there? 6B. Do I have a data sheet? You want to, so there's a data sheet and register map. You want to look at the register map to find out the addresses for each register. Good. Oh, interesting. Things here. 6B. What is B? What is B in binary or in decimal? B. Yeah, 11.
I was like, that's not a number in binary.
Pop-up quiz. So 6B is a device reset. There's 1 bit is a device reset, right? But all the other bits, we are not using them, so we just give a 0. But however, you have to give a 0 to put a 0 here to reset it. So that's why in the code, after we claimed, or after we give the address, sorry, where's the code? Yeah, after we tell the device the address, we directly send the data to it to reset it. So I have to reset it to make it work. Okay, keep in mind. And that's acceleration configure. So we are using, so I'm putting a 0.8 here. So 0.8 means it's 0, 0, 0, 0, and 1, 0, 0, 0, right? So it's 0.8. This is 8. This is 0. Okay. So which option we are using for this case? If we put a 0.8 for this register, 1. Okay. Is that 1? There's 0, 1 here, right? This is going to be a 1. So 1 is going to be this, right? We have to divide our reading by this number, 8192. Okay. 8192. So you have to do it here actually. This is just giving you a binary number, but you have to divide it by 8192. Okay. Another thing, we have to look at the code first. Okay. How do we measure the angle of the car? So when the car tilts, there will be a very small angle. Okay. Because the angle is tiny, so sine theta and tangent theta are almost the same. Do you agree with that? Because these two lines are almost the same length. All right. So if you want to calculate the acceleration, it's using the angle. No, if you want to calculate the angle, you are using the vectors of the acceleration in this direction. Just imagine that the angle is tiny, right? Super small. So you're using the vector here. Divided by this. You know what I mean? But vertically, it's always 1g, right? Because of the gravity of Earth. But it varies slightly. That's why it's better to still read it from the sensor instead of directly using 1g. It's giving you more accurate data. So you are reading because you can see the arrows on the board or the sensor. So you can actually tell that it's this direction, for example. So the reason I put a Z here is because I inserted sensor vertically perpendicular to the board. So Z is actually pointing forward. Okay, but in our application, we prefer putting it horizontally in parallel with the board instead of standing on the board. So it won't be Z anymore. So it can be either X or Y, depends on the orientation of the board you put on the car. All right. So this will be Z, no, X or Y depends on the orientation. Okay, so it's going to be acceleration X or Y divided by here, which is Z, right? So it'll be this one. So in example code, it uses tangent function instead of sine. But if you replace it with sine function, also works because this line and this line are super close to each other in terms of length. Because the angle is tiny. Okay, it's only tilts a little bit, then you want to adjust it. So the angle is tiny. That's why a sine or a tangent will be the same, give you a very similar result. We don't really care. So you can either use a sine or a tangent. And for here, even though I put a 1g here, but probably you want to read the data instead of 1g to make it more accurate. So in here, you can see it's a tangent 2. That's a tangent function in Arduino header file. And I think it's AY divided by AZ in the function. Okay. And this function returns, so it's just giving you a tangent data of AY over AZ to provide the angle. All right. And the angle is in radians instead of degrees. So you have to use this data, the arc tangent data, the radian of the angle and convert it into degrees. So put this data here in this function and times this number. So this number comes from 360 divided by 2 pi. Okay, this is how you convert radians to degrees. Okay, so you're getting a degrees. You're thinking I'm done. I'm getting the angle here. So if there's a little angle like 1 degrees, I'm going to adjust my wheels to balance the car instead of making it worse, right? So this probably will fall forward to make the angle larger, but you can use your wheel to balance it. So that's how that works. You have a target angle. For example, it should be 0 ideally. Okay. Whenever the angle is larger than 0, you put into a PID controller, then you adjust it. You rotate the wheels to adjust it. That's how that works. And so we need to know the angle first. We need to use the loop of the microcontroller to monitor the angle really frequently. The microcontroller can run the loops really fast, right? You're thinking, hey, I got acceleration when it moves or when it's falling in one or two directions. It's going to generate a acceleration in that direction, and I'm using that acceleration to calculate the angle. Seems like it's reasonable and seems like I'm done. However, according to the theory here, only use acceleration to calculate the angle, it will not be accurate. You can see the explanations here, I think. Yeah, it drifts. Data will not stay at 0. I haven't done an experiment to compare the data. If I only use acceleration or only use the gyroscope to calculate the angle, and what's going to be the difference? I didn't do the comparison. And I think many years ago when I was doing my controller board, the robot, using a acrylic board, I didn't use the gyroscope data at all, actually. I just used the acceleration angle, and it worked. But not perfectly, but even better than the tumbler car that people are doing, combine the two data together. So who knows? I mean, let's just follow the tutorial and just use whatever is considered as a better choice. So this is not, you're not done yet. You got a degree or angle of the car from the acceleration data. Okay, you're done with that part. And then you have to move to the gyroscope data. So remember the airplane, you got pitch, roll, and yaw. Okay, so for this one, which if we are assuming that the z's in this figure pointing forward is the front direction, okay? So when the car tilts, is it yaw or roll or pitch? Seriously? Yeah. Are you going to have a like yaw? Do you need a yaw at all? It's turning, but you're not using the turning data to calculate the angle, do you? Turn just turns. You just turn the wheel, right? But when you're calculating the angle, you're using the pitch direction, right? So because the acceleration board already shows you the direction of the yaw, and it's actually the roll and pitch, right? So in that case, for example, I'm placing this board in the car, and this direction is the front of the car, okay? So the X points the front of the car. Which axis gyroscope data that I should use? If you want to calculate the angle change. Z, Y, or X?
Facing forward, right?
Yes.
That's the line.
Yeah. Make sense? Because when it tilts, it rotates around y axis. Okay? So you need the y's gyroscope data, but nothing else. Now let's look at the map of the register. So this is a little experience from last year, and people had a lot of issues with extracting data from it by directly reading data out of the registers. It's very interesting. So the designer plugged in 2 bytes in between the acceleration data and the gyroscope data. So if you directly read, like for example, there's a Arduino function, you can read 1, 2, 3, 4, 5, 6, like read 6 bytes. You are thinking read 6 bytes, just do it, read 6 bytes. So I'm collecting all the acceleration data, okay? And read another 6 bytes, I'm gonna get all the gyroscope data. What's gonna happen? Yeah, temperature, you have to skip the temperature. It's continuously reading all the bytes. After 40, it's reading like 41, or 41, not 41, sorry, 41, right? It's a hex number. So reading 41 and 42, and then this. It's losing the Z data and reading the temperature and place the temperature data into the gyroscope register you have in the code. Keep in mind, have to skip it. Make sure you are having the correct address for the registers. So in that case, the case we're looking at, for example, the X is pointing to the front of the car. Then we are only interested in the Y gyroscope data, which is the Y gyro Y out, right? Gyro Y out. So you have to directly jump to this register's address and read it. Okay. And there are some mysterious code that I don't know, like if you need to change it. I also have my calculation from old design that I forced the loop time of the code. You can set up a timer. If it's not reaching, for example, I used 40 milliseconds, I think, for the whole loop, entire loop for the whole entire code. For example, it's reaching the bottom of the code. It's probably like 20 something milliseconds. And I delayed it for another like 10, 12 milliseconds to force it to 40 milliseconds. So I know exactly every loop, it takes 40 milliseconds. If sometimes it takes longer or takes shorter, I'm going to delay it until it reaches 40 milliseconds. So I know exactly the loop time. So in that case, because the data being read into the gyroscope register is this many LSBs per degree per second. It's an angular velocity. It's not an angle. It's a rotation. It's a dynamic motion. So what's happening is that the data is changing all the time, and depends on the speed of the rotation. Keep in mind, it's not like the acceleration, just one data. The gyroscope data is a angular velocity. It's degrees per second. So you read the data. So your Arduino is a digital system. Okay, you read it in this loop. You read it. Okay, you get the data here, and then it comes back to the top of the loop in the next loop, and then it reaches the point, that same point, and read the gyroscope data again. If you want to calculate exactly the angle that happens, angle change or the delta angle, you have to know the loop time, right? Because the data you are collecting is how many angle per second. It's a velocity, so you have to know the time. In order to times, you have to use the data being put in the register times the loop time, the second time you read it, right? To find out the angle change, the delta angle. So in that case, in the old design, I don't have the code being posted here. I forced the loop time to be 40 milliseconds. It's actually 4 milliseconds, actually, right? Doesn't matter. It's just 4 milliseconds for each loop. And that's the raw data being stored in the 16-bit register. Okay, this is directly whatever you read, the binary data from the register. And I have to use this, the loop time, divided by this parameter here. Okay, it depends on which one you choose. Okay, you can set it up in the register. So for example, I'm choosing the first one. Okay, the full scale range depends on the rotation speed. Okay, I'm not expecting my balancing robot is spinning that fast. It's not a helicopter. It's probably tilting. It's pretty slow. So I'm just using like 250 degrees per second as a full scale. Okay. Um, so what's the drawback if you use 2000 degrees per second? What's going to happen? You just get a more scale, a bigger scale range, right? Bigger range for the detection. So why we don't use the biggest range, which covers all the angle changes, just in case the car spins so fast, right? For some reason. Why we don't the larger? Why don't we use a larger range? Uh-huh. Yes, so you got a better resolution. So it's like you have this much range, and you're only using here. You only have like 16 bit, right? 16 bit, 2 to the 6, 16 steps to resolve that range. If you're only using this little bit range for the full dynamic range, the resolution will be low. But however, if you it won't be more than like 250 degrees per second. And it's going to be here, right? It's probably swinging 50, 60% of the full range, will give you a better resolution. So use the loop time divided by this parameter is what?
Angle per
Hmm? LSB, wait, let me see. Wait, should I divide it by it or times it? I want to get rid of the second right now. Wait, so if I do this calculation first, right? If I do this first, so I'm moving LSB to the bottom and move the degrees per second to the top, okay? And second will be canceled, so it gives you degrees per LSB. And then times LSB will give you degrees. Make sense? All right? So you are treating degrees per second as one entity, right? And this is LSB's divided by degrees per second, okay? So by using second divided by this whole thing, you are moving degrees per second to the denominator on the top, and it's going to be degrees per second per LSB, okay? And second will be canceled because this is on the top as well. So it leaves degrees per LSB there, and then times LSB will give you only degrees. Make sense? Okay. So because this is just constant, this is loop times that I designed in the old code, all right? And I used this one divided by this number, and then I'm getting this number, this parameter here. It's a constant. So basically, in my code, right, I just use whatever I read from the registers times this parameter, then it should be how many degrees that just happened in between the two loops reading, in between the two readings. Okay. And I think this number came from summer calculation. This may not be accurate because the original code for the tumbler, I think, used these numbers. They must calculate it. So for example, you can set up a timer in your code, and if you think this is the code I'm going to use, right? So before you tune that parameter, you start a timers in your code and you find out how long it takes to run each loop. And then you delete it. And then you change the number here. You know what I mean? Did you get it? But this number came from the original code of the tumbler that we already changed the code a lot to make it from 10 pages to 1 page. So this number may not be the best number anymore. So for example, this is larger than the loop time. This is larger than the loop time. What's going to happen? If this is larger than one loop, for example, this is like 3 loops. What's going to happen? You are still reading that data every loop, right? But you are just times a constant that is not exactly what your loop time is. So you're getting a bigger angle reported. So you're not actually changing that much. The car is not tilting that much, but you are having a bigger angle there. Make sense? So I think this number is being used for all these people's code, and it worked. But if you optimize that number, may give you a better performance, I believe. Okay. So I think they directly just used that number from the code. They didn't even calculate it or measure it. How do you find out the time of each loop? Yeah, milling, right? You got a timestamp using milling. Reported twice.
That takes 4 clock cycles. That big? Oh man.
That's why it's, for computer engineer, it's going to be a super difficult question to answer, which is no. I mean the question is, how is a person who was born in 1965? Did you see that question online? Some of the videos posted. It's during an interview. It's asking a person, like how is that guy if he was born in 1965? Yeah, where was he born and like what time? Like if he was born in California, then we are right now in New York. It's gonna be different, right? So it's yeah. I think yeah, it's just a joke probably. Okay, now the complementary filter. Again, I didn't measure or test or compare if you use it or not using it. What's the difference? Since right now you have 2 different angle data. The acceleration is giving you a static angle, but also the gyroscope is also reporting angle data. Right? It's degrees. Both are degrees. Both are angles. Okay. So you need a data fusion. It's getting complicated, getting fancy here. But fuse them together. How to do that? So the acceleration data, this is your acceleration data angle, right? Calculate it, and you assign it to angle, okay? But you are changing it later, okay? So assuming this is the angle, it's actually just the acceleration angle, okay? So the equation for the complementary filter is you have your acceleration angle times a super small number, and your gyroscope angle, keep in mind, it doesn't have to be z, remember? For the example I gave to you guys, right? Just now we are looking at the front of the car is x. So here we should use which gyro data? Y, right? We're just looking at y. So you got the y's gyroscope data, and it's being added to the acceleration's angle, and then times a bigger number. And keep in mind, you don't have to use like 0.9934. I don't have to use, it's just you're adding them together, it's giving you a 1, okay? And it's called a complementary filter because it seems like it's trying to, wait, will that be correct? I don't think you should put a acceleration angle here. You know what I mean? So what is this trying to do is, because these two measurements are both the angle data, right? And by using a filter like this, is actually reducing the weight for the acceleration. For example, the acceleration changes a lot, but I don't trust it, so I just times like 0.0066 to reduce the impact of that change to the overall angle. But for the gyroscope, I think it's more reliable. Then I'm going to use the ratio here, the weight, right, times 0.99934 times that angle. So the impact from the gyroscope will be bigger than the acceleration data. So I've seen all different formats of the complementary filter, but most of them didn't put the acceleration angle here, because if you put it here, it's going to be bigger than 1, right? It's going to be larger than 1. Why? Because let's assume this angle and this angle are the same. For example, gyroscope and acceleration are representing the same angle. This is larger than 1. Yeah. So I'm not sure if this is correct. Okay, this is from Kelvin's code. You may try to not including this angle here and see how that works. Okay. But I think put a bigger ratio for the gyroscope data is the most commonly used way to do it. Reduce impact from the acceleration, but increase the impact from the gyroscope. Okay, so you fuse the data, the two data, angle data, and put it into the overall angle. It's very interesting because it's running all the time. So this angle will be put back in here for another round of calculation. I don't know which one will be better. You probably don't want to include this one here. But if the tumblers, whenever you are not seeing a better performance, you just trying to modify it a little bit. I don't think I have a exact perfect solution for this specific project because it's being affected by so many different factors. And try different numbers, okay? And try to not using angle in here and see what happens. And the PID controller, if you haven't taken this class, so come back to the 351's lecture regarding PID controllers. So P is a proportional, integral, and differential, because it's affecting the stability of the system in different ways. So for example, we have a setup value here, all right? That's the setup, that's the goal, right? So for proportional gain, for the proportional term, it's just measuring the reading. So the reading, right? Reading times error. Reading minus target, right? Reading minus the target. So it will be for example, we have a reading here. It's going to be the error between these two. So that's the error, right? That's the error. So the proportional gain is going to times the error by the gain, right? So for example, it detects the error here, but times like 3. Usually it's less than 1. Times 0 point something. So it's moving proportionally, linearly towards the goal. and because the computer can run pretty fast, just keep increasing. But the thing is, it's proportional, so it's very likely that it's going to overshoot, over adjust. And then it detects a negative error, so it's going to pull it back. But very likely you'll never reach the goal because it's linear. It's just adding and minusing. It's going to oscillate. So you're not getting a really reliable system. So in that case, we need a nonlinear adjustments. You can use either integral or differential gains or components. So it's actually integrating the errors over time. So in our digital system, we are just adding them together. So integration is just adding them together, right? Just adding all the past errors together. And differential is, what is differential? Differential is going to minus the previous error. So if you think about that way intuitively, what are the three gains actually doing in the PID controller? So the proportional gain is really straightforward, right? Just very brutal force, right? Changing it back and forth. Linear, not good, right? So what you want to do is actually eventually, hopefully the controller can make this. Ideally. So you need the integral part, the differential part, and the linear part. So the linear part will bring it back to the goal pretty quickly. And the integral part is doing what? Intuitively, let's think about it. So why, a lot of times you don't even need the D component. So just use the PI controllers, it works really well. Probably it's gonna be the same case for our car as well. We don't use a D component, just use a PI controller, it works. Sometimes use a PD controller, it also works. The best performance probably is you have to use a PID, all of them. So for example, we are only using a PI controller, integral as well. So keep in mind, integral is actually adding all the errors together. So what is that saying? What is that helping the controller to move towards the goal? The integral part. What's really happening? So proportional is just a linear. Okay. Okay. What about integral? No, integral is adding the errors together. Yeah, continuous adding the errors together. So if you have a big error, okay, and since you have all the PID parameters already set up, or PI already set up, so if it's linear, just doing the linear job, it's not changing too much. Okay, just a line. Okay, a line, reaching the goal. Okay, can overshoot. If you're adding I to it, okay, if your P is too small, it's adding every little error, making a little adjustment, so it's getting very slow. Okay, so if your I detects it, so if the error is being added together, still not changing too much. Wait, I don't know if I can explain that intuitively. Is D trying to make it aggressively or I?
I is the one that reduces steady state error. I forget what D.
That's what I'm thinking, right? So is that making it more aggressive or making it slower? That's what I want to think about. So integral make it slower or faster.
I think it makes it slower.
Yeah. Yeah, because integral is adding errors every time, right? So if you have a small, or for example, if you have pretty big steps from the linear gain, then it's adding really fast. It's even faster for the integral part. I think it's more aggressive, right? For differential, right? For differential, if it detects the error is getting smaller, then you slow it down, right? For differential, because it's doing subtraction. It's trying to do, so the subtraction is every time, every single moment you detect the error here. So whenever it's approaching the goal, you have a smaller error, then you subtract a smaller one, or adding a smaller one instead of doing a linear increment. So that's why for the differential one we use a subtraction here instead of adding to it. So it's hard to tell, if you're just assigning random numbers to the gains. It's all about tuning. So that's why I'm adding one task here to assign the pin of the microcontroller to the encoder, so you can actually tune it instead of randomly change and reprogram the microcontroller to shorten the terminal time. You know what I mean? So you don't have to reprogram it. It's just a tune your encoder to change the PID or PIs. Just make it simple. Starting with P. Okay, you have to tune P first. When it's stable, then you start tuning I to finalize it. Okay. So we are here, right, for the data fusion. And for the PID controller, it shows the equations to calculate PI and D gains, the parts. These are the gains, right? KP, KI, KD, the gain. So if you refer to here, you can see the every time the PID, you just add them together, and you're basically adding this, and this together. So it's going to be KP, the gain, times the error over time, and Ki times the cumulative error. This is differential error, which is error difference. Yeah. And these are the implementation of the PID controller in C language. I think it makes a lot of sense until, okay, so integral, see, it's just adding together, right? It's adding the old code, but however, you have to limit it within minus 100 to 100, so it's not giving you a crazily big number to spin the motor super fast. So are confining them in this range. So for I, you use the gain times the integral, which is the datations of all the old errors, and you use a KD, which is the differential gain times the angle minus the last angle, the difference. Okay, and eventually you put them together. Okay, the P term plus I term minus the D term. And Kelvin was asking, could we use plus the D term? I think when it overshoots, you need to minus it. When it's not reaching it, you need to add it, right? So I think both are fine. I'm not sure actually. It may slow it down. It controls in real time. You want to run it fast. So I think we can keep this minus sign here for now. So don't change too many variables. And it has a little counter here, a count plus 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 1 here. If the count is equals 2, it clear out the count. I was thinking this probably came from the original Tumblr code. So why is trying to do this? I think it's not trying to adjust the car too often. So adjust it twice, then I really apply the change to the wheel or to the motor. So it's not jittering, I think. You can probably tune this number and to see the change. And I think after that, which is a part that I don't really understand, it's exactly the same filter. You see, it has a filter fusion. Here, you get another PID. So just recalculate the PID by from the PID value here. It may affect the stability a little bit, but I think this may not be necessary. I don't know. So this is what you can test on your side. I can understand. So we can understand the code. It's just another filter, right? It's trying to filter the gain. It's a complementary filter. And why do they use it? Probably the engineer in the company in Alago who designed all the tumbler robot, they probably apply another complementary filter and seem like it's getting more stable. But if you are using the stepper motor, it's more accurate. Maybe we don't need this anymore. Okay. So for my old code, for the stepper, by using the stepper motor as a motor for the car, I didn't use a secondary complementary filter. It worked fine. So it's your choice. Okay, if it's not working, then probably try to use their modify their code a little bit. Okay, it's just modifying the data. It's not doing anything else. Just modifying the data. That's another PID here. So the output is done already, but it's doing another PID here again. And the KP is a smaller case KP, a KI. Seems like it's not a KP KI here, but it's a I don't know if they are declared somewhere else. It's probably you can find it from Kelvin's code and see if that makes sense. Okay. And the rest of the code here is just the PWM. Okay, so they convert the PID controller's output into the PWM data, and then you use the PWM to drive the motors wheel, the motors. Okay, this is just a control pin on the driver. Okay, you can easily tell what they are. So enable that motor and write this PWM data to it. This is writing to the motor. Okay. And for initialization and interrupts, if you haven't worked with interrupts, you have to go to this tutorial. And I believe in that semester, I have a recorded lecture that I can watch in order to understand, if you scroll down here, to understand what are these things. Okay, important. And how to calculate the timer for the interrupts. How to use this equation to calculate the time, the frequency of the interrupts to be triggered. Right, not too long, and I have recorded lectures to explain it. So the car initialize a lot of functions and also the interrupt registers. Because this flag is triggered by the interrupt timer, according to the parameters you set up over here, I think it's 100, and you put into the equation that I just showed you in the data sheet to calculate the frequency of it. So every time the interrupt is being triggered, it balances the car. So I believe this is within within 100 milliseconds. So I don't know if you plug in this number, what is the time is, but it just runs the balancing code, which is whatever on the top, or the PID and the reading, the angle, gyroscope. It runs that code every time it interrupts the computer system and execute this interrupt service routine. Again, most of you took microcontroller in the past, but Jesse, please ask any question you may have for interrupts and refer to the tutorial over here as well. Okay, and there's a recorded video. I think you can go to my website and just find out that class, and there's a recorded video over there. Let's see. There are 3 versions of the code, and I don't think Kelvin's included the joystick microcontroller's data or code in there. So the code here is totally just for the car. I don't know if David or Brady, they have both code for the controller and the car posted over here. But I think the joystick controller's code is very simple, just sending numbers through the 2.4 gigahertz. Right? All right, start the long lecture. Any questions by far? Expectations? So what we are building eventually, make it simple. What we are building using. So we can use ESP32 or Arduino, right? And it has to be a PCB for the car and a PCB for the remote controller, yeah. And for demonstration, you can plug into the breadboard. Doesn't matter.
Why can't we just use like a PS3 controller?
If you want, but it's just more expensive, I think.
Not really.
Not really. How much is it?
Yeah, $50.
For a PS3 controller?
Yeah, but it's still like $20 compared to how much is the joystick?
One. It's free. I have 100 over there in the lab. So it's gonna be you are going to use a frame available in the lab and use the NYMA 17 stepper motor and remote, and it can be ESP32, can be ESP32 CAM, can be Arduinos, can be the 2.4 gigahertz RF modules. And I'm not going to have you guys do a presentation in the finals week. But we're having multiple presentations before that to keep you guys on your toes. It's good, right?
I know. I was excited. Oh, perfect.
You want to start working on this huge project just in the very last week, right? So we are actually doing multiple presentations. All right. We are not doing a presentation. Is today Thursday? Oh my goodness. We're not doing presentation next Tuesday, but we are next Wednesday, next Thursday. So you should have a lot of things to present. Yeah, 2. Yeah, 2 and 3 actually. The one more after that.
Yeah, I just didn't know if we needed to like 1 day space.
But the project's due the week after that. So it's you guys probably need to spend more time on it. Oh, finals is finals week is week 16th, I think. Is it? Yeah. Let me take a look at it.
Wait,
How much did we get?
just read the email. It tells you why.
Yeah.
Wait, before we get the money?
But they're gonna let you resend that.
I mean, everything else passed except for the internet.
We should.
What did yours, what was your grade?
Wait,
they like grade
it
it?
right after our time canvas.
I guess we were something.
Proposal for senior sem?
Yeah, I made a mistake on the,
Oh
my. No, they don't, I didn't
Wait,
make a
wait, wait.
mistake or something on the freaking massive thing. That spreadsheet, but everything else is wrong.
All right.
It would be so funny if your group of all the groups didn't get funding though.
You're not going to spend a lot of money.
Your group is the tryhard group. It would be such a flex.
All right, guys. Is that 12:40 for the end of the class?
I don't know.
12:40, I think. 12:40. For minutes. Let's just wrap it up. Okay. So the finals week is week 16. Okay, and we are not having a final exam. So we basically after the Thanksgiving break, every single lecture, every lecture's time will be a presentation. I'm gonna check your progress. We'll see. It's a pretty complicated project, actually.
Wait, how do you see?
Questions on this project? Expectations? No? All right, let's go to the lab. I'm going to show you all the parts. Okay.